So hi, I'm Mike Groskoff. I used to be a PhD student at Simon Fraser in Vancouver, and at the time went to the data science reading group pretty regularly and really enjoyed it there. I've since moved off to now be a statistician somewhere in the desert. You might be able to infer where through these slides, but I do statistics and physics and engineering problems. And so today I'm going to give some slides about, this is technically not a Kaggle competition. It was a top coder competition for assorted reasons about bid processes, but it's a data science competition. I'll talk a little bit about the competition, and I'm going to just talk through basically the story of what me and my team did in going through and doing this. There were two versions of this competition. There was an intra-lab competition an interlab competition. This was a number of different research labs in the States had teams that competed about it. And then after they did that, they ran a public version of it, which is the one on Top Coder that the link is for and all that. In the public competition, I actually only got to basically use the model as it was at the end of the interlab data competition. But so the story is mostly going to be about how we went about it during the interlab competition. Though I'll talk a little bit about what some of the about what at least the winning in the public competition did in sort of a bullet point kind of near the end.
Hey, Mike, your slides are not in full screen mode like you were showing before. I don't know if that.
Oh, really? Because they are for me.
Are they? Oh, okay. Maybe they're on a different screen. I think we're going to be able to see them. Okay.
No, I'll just share my full screen. Now do they look better?
That's better.
That's weird.
Thank you.
I was sharing just the
I have trouble with that
program, and apparently even though it was full screen, it wasn't for you. Okay. Yep. So this was our team for this was called Winning the Active Radiation Energy Hunt Outside Using Statistical Excellence. I'll talk more about that in a second. So the data competition, the idea was to try to find radiological sources in an urban environment from just detector measurements. So this is all simulated data. This was not a real urban environment, nor real radiation sources in urban environments. It would be kind of unethical for someone to put them out there to test. But this was so they had generated these synthetic city blocks with different building material types, different plot types. And then in some of the cases, they just have a simulated car drive down the street and pick up, gamma detections. And some of them, they would have a radiation source. And so each simulation each data stream, they had, I think it was 9,800 9,800 time series. Each time series was a large but irregular number of points. And it just simulated a vehicle driving down the city street with a thallium doped sodium iodide detector doing gamma ray detection. So as I said, they simulated these different types of things. So some parts of the street would have soil and brick and granite. And this was all communicated to us that this is how they had generated the data. And they said the vehicle was kind of in a constant lane, driving at some constant speed, but the constant speed might vary. So the way it moved through the environment might vary. The street geometries would vary from time series to time series. And then they had a number of possible sources. So the idea was detect, is there a source or not? And I'll say this again, because I will admit I've only gone through these slides once since I gave this talk 3 years ago or 2 years ago or something. So, they had a few types of sources, and they wanted to detect, is there a source? What type is it? And where is it? So the parameters that they used to generate, they had a type, they had a strength of it, they had shielded or not, and then they had some location. So we were trying to say, is there a non-natural source? And then there is a different penalties for different ways of getting it wrong. If you had a false negative, you got penalized more than if you got a false positive. The P is just that there is some proportionality number that they didn't want to say for some reason. So you got penalized twice as bad for having a false negative. So for missing a real source than you did for declaring a source is there when it wasn't. You also got a penalty if you got which type of radiation source it was wrong. I'm letting out my cat for a second. And you also got penalized if you were far away from how far you were from the source. They didn't say what the decay was, but they said you got penalized in a distance up to a certain penalty if you were too far away. Effectively, if you were too far away, you were basically considered a false positive. Although not penalized for that correctly for that, as you can see, because it was 4p instead of 2p. So I had a team of 5 of us, a few early career staff members at a desert research lab, and a couple postdocs, a postdoc and an undergrad. We were all in a physical warehouse. So this is where we work. It is a lab. We were all in a warehouse out here, which is where new hires were located for a while when some various sorts of administrative stuff was being processed. It usually took about 6 months. And so a number of the new people or people who weren't going through those steps just worked in a literal warehouse. And so we named our team as such. All right. So what's the data that we had? So like I said, we had 9,800 training runs, and then 15,923 test runs for the, that was a combined, that test data was a combined public and private test set. So when you'd submit your predictions for the test set, it would give you a score back for the public part, but it wouldn't tell you the private part, as is standard for a lot of data competitions. So we'd have training data that was labeled. This data was a time series of a gamma ray energy and a time from the last observed gamma ray detection to the next one. So basically, you had a number of times, and you had a number of energies, a number of photon energies or gamma ray energies.
Hey, Mike, I have a question.
The labels, let me just finish the one thing here. The labels then, so you had this full time series, and one series looked like this. So energy is on the y-axis here, and time, rolling time, the cum sum of time is on the x-axis. And so you can see the energies varied over time. And then our training labels were just which source it was of 6 sources, and what time the vehicle was closest to the source. Those were our 2 labels. And then we had all these run IDs. What's the question, Bruce?
So you described how this is all synthesized data, and maybe you answered this already, but did they model like background radiation, just natural radiation as sort of noise that would interfere with this?
Yeah. So these gamma rays aren't all from a radiation source, or it would be really easy to tell if there was a source or not in some sense. So there was a simulated background that they didn't say anything about, but there was a simulated background that you could learn from the cases with no source, with source ID of 0. You would effectively be seeing some background. They didn't say anything about whether the background was constant between cases or if it varied from case to case in any way or varied over time. It certainly varied by what type of geometry of building was around. Because some buildings, if I go back to so some buildings like granite buildings tend to give off more radiation naturally than say a soil plot, if I recall correctly, or brick. I could be mistaken on that. Physicists listening might be realize it might be noting I'm wrong about that. But the basic idea is that as there's some just general background there's some background that these buildings and other things emit. And so they come together to generate some counts. But then there also might be counts from a source or not, depending on whether there's a source there.
What are the energies of this radiation? Do you have any idea?
Yeah, so we were given how much time it was from one gamma ray count to the next, and we were given an energy in keV. I say keV, pretty sure it was keV.
Yeah. It's KeV, but what is the value of this energy? It's close to.
I'm sorry if the y-axis here isn't very visible. So this is so it ranges from something low to 3,000, about 3,000.
No. I can see one patch around 1,500. Is that correct?
Yeah. So if you're looking horizontal over time, there's like there's like a peak there. There's clearly a peak where there's more counts at about 1,500 keV. There's clearly another thing down here at like 700 or 600.
I think that is the potassium line, maybe 1468. I think so.
The what?
Potassium background. It's basically coming from this different color of this of the building. So that is the major source of potassium. I think it's a potassium line.
Gotcha. Yeah. So we weren't given the background, what the background spectra looked like, but we were given what the different sources, like an idealized spectra for the different sources, and I'll get to that in a second. But yeah, so that's the data set though. 9,800 time series that were some length, usually pretty long, tens of thousands of observations, if I recall. And then the labels were source ID 0 if there's nothing, 1 through 6 if there's something, depending on which one. And for the ones that have a source, what time in the run was the source closest to the vehicle? So the team started with a couple quick things. So one of the team members, Devin, just did some things where he basically like binded up in energy, it says bind energy, but what he did was average in energy and then plotted over time and did a basic like change point detection to look for, was there a change in the average energy or and other things like that. He binned the data and pulled out a bunch of features. So extreme values, peak. He basically did some manual feature extraction, and then put that through a classifier, and he did okay, but it wasn't. It was. So the scoring is on a 0 to 10,000 scale. I won't say what the final score was, but I'll say it later, show it later. But so we had about 3,000, so it was okay, not awful. We started looking at the spectrum, so we saw that the general spectrum looked pretty consistent from run to run. If we took all the clean runs and averaged their spectrum over time, we could see that the spectra varied a bit. Those aren't constant, totally constant, but they're pretty consistent. So we felt like it wasn't unreasonable to treat that as sort of a constant background. Then we had these spectra. So we said, okay, some of us have a little bit of physics background or general knowledge of spectra background. And well, if we have a source, then the detection the counts we're going to get is going to be the background plus whatever the source spectra is. So let's treat this as a mixture model. Let's just do a simple mixture model where we have the total spectra is the source with some weight and the background with 1 minus that weight. We know that there's not anything that has more than one source because of the labels. And so, we're not worried about seeing extra sources, except as I'll say in a second, one of the sources is a mixture of 2 of them. So we have 6 total sources, but really it's 5 unique ones plus a mixture of unknown proportion of 2 of them. So we thought, okay, let's try a basic, we have an idea of what the generating process is. Let's try to model it that way. And we looked at some of the data and said, okay, some of these are kind of easy to spot. If we take this background plus this source's spectra, this was source 4, we looked at one of the runs that had source 4 looking in a block around the labeled time. And you can pretty well make out that there's this peak, but then there's this big peak from where these two peaks are at. We don't actually resolve the 2 peaks, which we found, which was interesting, but we see clear signature of that being, of a mixture model kind of being an okay thing. And don't worry, I'll get to the machine learning, not just talking about this stuff, but yeah. So we had this other source, that was a mixture of
May
source
I
1 and
ask you
5.
one question?
Yep.
So can you go back to the slide, previous one?
Yeah. There.
Yeah. What is the meaning of this big peak in this in the around 0 or maybe 250 keV? What is that meaning?
This peak, this was from the background. This is just that was the dominant peak of counts that we saw in the data.
Okay.
I'm turning on the light now because the sun's going down on me. Okay. I'm a time zone ahead of you, so.
Yeah, this is a sodium iodide spectrum. Am I right?
But I don't know. I don't remember which source this was, so I can't.
No. I am asking you, what is that spectrum? You use sodium iodide thallium activated detector?
Oh yeah. So the detector was a sodium
iodide
detector, thallium sodium iodide detector.
So if you use the germanium detector, you can get a very nice resolution. So these two peaks can be resolved in germanium detector.
We didn't have control of that. That's how they generated the data.
Okay.
This was we weren't choosing the detector and stuff. We were just given these time series.
Okay.
And that information about how it was generated.
Okay.
So we said, okay, we have this structure of data. We have this other source that's a mixture. How do we want to handle it? We thought about, do we want to treat it like just 50-50 and treat it like that and hope that was good enough? Do some other combination, do some Bayesian stuff that I'll talk about in a second. But so we figured, okay, we have a physical generating process. We should be able to deal with, treating it sort of like the physical generating process should help us with generalizability. We know that the test set, we know that the hidden data might be a bit different than the data that we have. And so we want to make sure we generalize pretty well. So, we're going to try to handle this phenomenologically. We're trying to handle this in a physical, in a generative model, a physically generative process. So we thought, okay, this is a basic mixture model. This is easy to do. Bayesian inference, we're statisticians. Bayesian inference is great. So we say, okay, look, we're going to bin this up into the time up into Windows, and we can just do Bayesian. We can get the posterior probability of each mixture. We can get the probability of just background, the probability of background plus source 1, background plus source 2, and then we can compare the posterior probabilities and say, pick the high probability model or do, say there's a source or not, detect source probability of source or not, and then do if source, then which source. We could do either way about it. And extra conveniently, we have a decent amount of data. This is a pretty big data thing. So, because the streams were so many observations. So, but we can do this integral ahead of time. So the computation can be actually really quite fast for each case. And in a sense, there's nothing to train. Hey, this is even easier than machine learning because, we don't have to train anything on this on some level. But that's not really the case. We end up being kind of naughty Bayesians. We for instance, we had these windows. We didn't have a good way to decide, we don't want to treat each time window independently because that doesn't seem reasonable, especially, because the vehicle's driving by, the sources might be related. So we try to do some kind of hacky, the prior probability for the different models is basically the posterior from the previous step plus a fudge factor to make sure that low probability models still can show up if the data says they should. And so we had this kind of hacky time approach. And also, I mentioned we have this weighted mixture of a background plus a source, but we don't have any information about what that weight should be. And sometimes Bayesians will say, if you don't know, put a uniform 0-1 prior on it. That's a uninformative prior, but it's not really uninformative in this case. It's saying that there's just as likely to be an all source spectra as an all background spectra, But we know that's not the case. Like even when you're close to the source, you're probably going to have a lot of the background in it too. And so we tuned the some of the priors for our Bayesian model. So we tuned what the weights would be, or what the prior for the weights was, to make the model work well. So we're training a little bit. And we tried it out, and some of these worked really well. So training run 8, started with the no source, and then boom, it says a source. It interestingly changed which source it thought right when it passed. So the labeled time when the source was closest was right there. So the vehicle's driving up, got to there, and then all of a sudden the model thought it's a different source. That was odd, but we were like, okay, that's fine. We'll just pick whichever one had sort of more probability and go with it. And that looks really good, right? It's detecting right around the labeled time, and it's detecting the right source in this case. Another run, right at the right time, it kicked in and said, oh, boom, there's a source here, right when that started. Well, now there's 2 different things going on, because this one kind of liked it being in the middle, and this one liked it being at the front. And this other one also liked it, but it worked pretty well. These are pretty good, for a model that has very little training. We looked at the training data and it looked pretty good. We thought about how, we know how we want to pick the source in some level. Specifically, if the source, the probability of a source was more likely than not a source, then pick a source and then pick whichever one has the highest probability. Or strictly speaking, we picked whichever one was close to 1. And if none of them reached 1, whatever is the highest probability. So basically whatever was the highest probability. And then for the time, we, instead of looking at that probability model, we just did a quick optimization of that mixture weight and found when the weight was the biggest. And that actually worked pretty well too. So we had these curves of the relative weight. And you can see that the weight of the back of the source spectra peaked up around the right time here, and peaked up around the right time here, and these are all pretty good. It wasn't actually as good as it looks there, because of the way the penalty for the times worked, being off by this was off, as good as that looks, it was still off by like 10 seconds or something, which made it actually penalized quite a bit for being off. The penalty wasn't wasn't scaled as nice as we had hoped. But okay, so we've got this. This isn't, there's not even really machine learning in this yet. This is just all statistics in a physical model. And we did that case, and we did a lot better than the simple classifier on some handpicked features model. Go ahead. Someone was asking a question.
Sorry, for the slide before that, about the incentives there, so would you still get points if you're off by a couple of seconds, if that's still a correct prediction of the source?
Yeah, so the way the penalty worked, your worst case was to say a false positive. The worst case. No, I get so false negative or being way off, and by picking correctly and being way off in time were both bad. I think picking the worst case was picking the wrong source and being way off in time, because you got the P penalty plus the 4P penalty. So
there's an element to bring it in. It's not like it to predict true all the time.
It was not good, yeah. So you couldn't just pick a source and predict good all the time, because you get hit really badly if you didn't know the time and which source. Gotcha. And if you always just picked negative, you'd get hit 4P every time, which is also bad. So yeah, the scoring was a little wonky, and this actually slightly changed on the public competition, because the intra-lab one was first, and we brought up hey, this scoring doesn't make sense, because they were saying that being far away with, if you predicted too far away in time, that's essentially like a false positive. And so we argued that it should have been penalized the same as a false positive, for instance. And yeah, so they worked out the scoring slightly different for the public competition, but it's basically the same. I think they just fixed that part. But yeah, so the penalty for being off in time was related actually to the distance. They said time, but it was really the distance you were off in the simulation. So it scaled, it was as you're moving away, as the car's driving by, if it's too far away in distance, which from just seeing, when you're just seeing the times, is effectively time too, but it meant it was a scale. It was a time that depended on the speed of the vehicle and the time of the run and stuff. But yeah. So this model did quite a bit better. It was almost 100% better on this scale. And so we were like, okay, this is quite good. And we tried some things about, well, can we bend the time smaller? We'll get more noise, but maybe we'll get finer resolution on some of the things that were not being seen, some of the false negatives. And we got more noise there. I can skip that, but going in time, we did actually get better. So we had this Bayes opt fixed 0.1 because we were using 0.1 seconds as the window and improved all this stuff, but we got quite a bit better. But we were still, so we weren't leading at this point. I noticed I haven't mentioned the team that was leading yet, so I'll get to that in a second. But yeah, so we thought, okay, well, we can do better if we be even kind of worse Bayesians in a sense, worse statisticians, because we're going to bring in machine learning instead. And so instead of dealing with just this nice statistical model based on the physical process, we still fit that, but then we take we bind some data features together with the Bayesian prediction. So we take our predictions from our Bayesian model, the probabilities, plus some of those features that were extracted before, as I mentioned, and we basically threw them in as features to a random forest and did classification on them. Why random forest? Well, we tried a number of things. We tried SVMs, we tried BART. I'll get to neural net stuff in a bit, but we tried a few things, and random forests worked really well. Those of you who know me from the other meetup will be surprised. We didn't touch Gaussian processes for this, not once, mostly because of the size of the data, and we didn't have a good package sitting around to do it. But yeah, so we tried some things, and we found that if we took our Bayesian model predictions and fed them into a random forest with some other features, we could do much better than before. This was, again, another step up of, so we went from 3,000 to 5,000 to 6,600 to 7,200. So, we're making some pretty good steps up here. And then we decided, and then one of us was thinking, we were like, Bayesian models, they naturally update as you collect data, right? You have some prior, you collect a new data point, you have a posterior, and you do that through. And because we realized the model selection, the Bayesian model averaging or Bayesian model selection was fast enough that we could actually do this in a very quick way by looking at one observation at a time. So we could stream the data in, look at one observation at a time, update the Bayesian model probabilities, and get a streaming Bayesian model that updated without any of the window binning. And so here's our log model probabilities. So like it starts and everything but everything's low except the background is high. And then suddenly this one source jumps up high and stays there. And then it drops down, another one jumps up, and you get all this noise. And our hope was we could get these curves and we could do a better job of picking out structure in these curves that we could chuck into our random forest that would be more informative, because this sort of model is going to really react really quickly to any changes in the data. It's going to, like when a source gets near a detector, it's going to be very sensitive to seeing a source maybe blip up for a little bit of time. So we fit these streaming models. We still stuck with the weights. We tried this cool streaming model. We're really excited. It didn't really help. We tried 5 versions of it. We tried doing it with, smoothing out over these curves after we got them. We tried mixing some things about them, and it didn't really help. But tossing in the random forest ended up, I guess, okay, so we actually did the streaming version without the random forest and it didn't help. Then we were like, oh, we can take this and plug it through that random forest again. So we took out some features from those curves. So we took out things about the average log probability for each source, the maximum. Actually, I think it was the maximum minus the average. So it was the deviation from average, maximum deviation from average. We took out we plugged these features from these model probability curves in. We got another good step up. We fed these in. We tried some other things. We tried gradient boosted trees, support vector machines. We tried BART. We tried, some other things. And our score with this moved us up into second place. I still don't have the other team's score in here. I thought I kept that running through here also, but I guess I didn't. So and then we thought, well, we're tossing all these things into I mentioned, we have this Bayes streaming model. We have this random forest that's meant to kind of to try to pick out some of the features and be an improved classifier. And that was okay. And we tried some other things, and none of these other things did better than the random forest. But then maybe even if they're not better, maybe they see it differently. Specifically, we were suspecting we were still getting a lot of false negatives. And so we thought, let's take some of the positives from the other approaches and see if we can add those in and ensemble them together. Or do a mixture where we basically get the predictions from all and do an even voting from each method to say which is the best. And we improved some more. Then pretty late in the data competition, somebody was like, well, we've been using this time approach for a long time, but we actually, we can see how far we're off in our time predictions in the training set. Let's just do a simple bias correction. So do a mean bias correction. So we just took the average that we were off by in the training data set in time, and we just shifted all our time predictions by that. We tried doing it as a function of some stuff, but it didn't turn out to help at all. So we just did a simple shift bias correction. And that actually put us slightly in the lead right near the end. This is probably on the last day when we're throwing all this like crappy, unprincipled ensembling of things together, just to see if we can bump things up a little bit more. At last minute, we're throwing these together. The final on the public score, this Lawrence Berkeley team led by Tenzing Joshi ended up beating us on the public board. And so, they were that was the team we were really competing with for most of the time that was doing the best. There's another team that was on there that was good. I'll get to them in a second. But, we took all these approaches, we ensembled all this stuff in a very unprincipled manner, but in a manner that made sense because we were sure we were just missing a lot of the positives. And we ended up just behind, so we saw the private set and we lost by 1 point on a scale of 7,000. So private score set, we lost 7113 to 7112, which was surprising. We were sure we were far enough behind that it didn't matter based on the public, but it was extra disappointing to see we lost by 1 point to the Berkeley team. There are a bunch of other teams that I've cut off because they didn't matter for the interlab competition. So our final model was this Bayesian streaming model selection approach, fed into a random forest, fed into an SVM, fed into what I call Devin 2, which was this model with the random forest plus a bunch of the features Devin had pulled out of the data. So crappy, unprincipled ensembling, but an ensembling that seemed to work. We just barely lost there. So some lessons that were learned: machine learning in tandem with Bayesian model selection did really nicely. And in fact, helped. We feel like the Bayesian model helped close the gap on the private set. So I think I might say this again in a few slides. So I apologize if I'm saying it now, but I'll say it again then. So one thing we suspected about the people running the competition is that they were intentionally going to make the hidden data sets extrapolate a bit. They were going to make them not just random samples from the same data, but they were going to make them harder cases. And so we, with that in mind, we really wanted to make sure our approach had something underpinning it that would help us generalize, that would help us with this. We're going to predict, be able to predict cases that are different than the ones we've trained on. And we think the Bayesian model did a big help with that, but the machine learning was important to it as well. And I'll talk about that in a second. The rest of this was just me talking about stuff we had. So we put this all, we wrote this all in an R package because we're statisticians and R was the tool of choice, all in a lab internal Git server with each implementation in this thing. So our thought on why machine learning was so important. Why did the Bayes and machine learning work so well together? And the thought was that the machine learning helped fix some of the hackiness from that we put into the Bayesian model. So like I said, we had this Bayesian model, and it's based on what the true generating process is from the data, right? We had a very good idea that like the data that we're collecting is these sources plus some background. And then over time, but we didn't really have a good way to deal with the time dynamics. The way we dealt with the mixture of the mixture weight for the sources was very, very hacky, or very, we had to train our Bayesian priors to do well. And we felt like that wasn't likely good. And there were probably better ways about that. There was a lot of stuff that went into it that was kind of, that there's a lot of approximations that the Bayesian model needed to have to be fit, that we're going to mean that just being a good Bayesian and saying a good Bayesian statistician and saying, pick the thing with the highest probability because that's what the data says. Well, we're pretty sure that wasn't going to be just good enough. And machine learning helped us classify better by fixing that, by correcting the Bayesian model in a sense. We tried a bunch of other things. Some basic stats things, some other things. One of which we just said, let's try like a windowed chi-square test because that's like somebody thought, well, that's like the most basic statistics thing you can do for like source or no source. Just like try to reject the hypothesis of it being a source only model. And we found that didn't work even in cases that otherwise we detected pretty well. We tried just fitting we had this mixture model and just try optimizing the weight over time and pick the source with the highest weight. And that did kind of well, but it didn't do nearly as well as the Bayesian model selection approach that we took. It might have had similar gains if we had done that and then combined it with the random forest. We never got around to going back to that in testing. We tried some things about the likelihood on some things to handle the dynamics better. We also tried a crude attempt at deep learning. And I say crude because I did it. But we thought, hey, we have bin counts over time, and we can just turn that into an image. We can just make that an image and then run train a convolutional neural net to identify sources in the image. That, we were like that should work. So we built the convolutional kernel to have some width over the energy direction and some time width that we wanted to. It was kind of like a tall, thin convolutional kernel because it was tall in energy and then thin in time, so we could detect quick changes in time. Tried all sorts of training this, tried playing around with that a bit, could not get it to do even close to as well as the approaches we had taken. So in the end, I was like, this data, I don't think it really lends itself to this very well necessarily because of some of the ways we were trying to choose the convolutional kernel and stuff. Turns out I was wrong. I'll talk about that in a second, but I was wrong that wasn't a great idea. We also did random forest stuff, tried to take the test statistics and other things from the previous slide, put them into the random forest and do some things, and that just didn't work as well. But that crude attempt at the deep learning came back to bite a little bit. I'll talk about that a little further in a second. So some things we thought about, like things we could have maybe done to improve it, that on the public competition I was tempted to do, but didn't have the time, which is why on the public one, we just plugged the model as it was fit on the interlab competition. And I think we ended up in 7th without doing anything different, even though the data had changed a bit. So felt pretty good about that, but not great. We would have liked to have been in 1st or 2nd. And then we also thought, is there a better way to translate these probabilities into machine learning features? We just picked out some features and plugged them into the random forest, but like this is a time series structure, maybe something like a recurrent neural net would have been able to identify the changes in the model probabilities better than the way we did. I think I did try the convolutional net on the Bayesian model probabilities as well, but yes. So this, I just threw this slide in. It's kind of crappy, but I just threw it in today because I wanted to be able to talk a little bit about what I knew other teams did. The team that won the public competition, and this is what I was kicking myself about that convolutional neural net idea, because the team that won the public competition turned the spectrum over time into images and fit convolutional neural nets to them, and did it well, or did it actually simpler than I expected and did better than our model. So what did they do? So I said, we were like, oh, let's reason about making the convolutional kernel, like, the convolutional kernel some width in time that would give us some specific type of time resolution and then some energy resolution vertically. So we picked the kernel, we tried different kernel shapes, but we picked it and picked the way we turned it into an image, the number of pixels, in a specific way to try to pull out what we thought we'd see in the data with the peaks from the spectra and stuff. The team that won the public competition just turned them into a 200 by 200 image, a 100 by 100 image, a 50 by 50 image, and fit 3 models. And they did a lot of good things about cross-validating, learning some of the structure, they obviously knew what they were doing and did it well. But the way they binned it into the way they turned the spectra into images was very just didn't respect anything about the fact that the things were different lengths in time and stuff. It was just turn them into 200 by 200, 100 by 100, and 50 by 50 images and run a CNN on them. I was shocked that did so well, but on the public competition, it crushed every other team. They put in their first result with 5 days left, and it was way ahead of everyone, and nobody else, I think, caught their worst case. So it does work. It did work for them. The team that beat us in the interlab competition, but actually did worse on the public one when the model was just kind of tossed into the public one, did non-negative matrix factorization. So they did a matrix decomposition approach on the spectrum data, or on the data, and then just used the weights of the learned spectra to try to identify when there was a source or not. It worked quite well. They also did the same sort of thing about doing that and then taking the basis weights and putting them into a random forest. So there was a common idea of, fit something kind of motivated based on the spectra and the physics, and then throw it into a machine learning model on the back end. There was one other team that I thought that did something that I thought was somewhat clever also, which is they fit a classifier for model or not and such. To get for model or not, to get a probability for a bunch of time bins. And then they smoothed that over time. And then they took derivatives and stuff. They took high order information out of the curves of their probabilities over time. And then they built a classifier on that. So they kind of did a classifier, smoothed the probabilities, did another classifier and a regression model to get the regression model for the time. And that did quite well for them too. It didn't do as well as ours or the other one. We did find one fun thing. We did find that we could get everything wrong and get a score that was technically below what they said the score range was, because they said it was 0 to 10,000 and we got a slightly negative number. You'd think, oh, we can, if we can get everything wrong, can't we get everything right? But actually, all we did is we predicted a source number that didn't exist. We predicted source 7, even though there were only 6 sources, and at time like negative 100 or something. And turns out that they hadn't programmed it to not accept those, or they programmed it to treat them as wrong. So that was a fun test. Some people supported this. That's the end. So thank you for all listening. I hope this was an interesting rambling story of how Team Warehouse approached this data competition, how we approached it, how we thought about it, and how we weren't very good statisticians, but we're good data competitors in it. So thanks.
Hey, thanks, Mike. That was great. I have a question, maybe a couple of questions, but I was mulling over this time bias that you discovered kind of experimentally. The techniques that you were using up to that point, were they actually time? Did they in any way incorporate the time evolution of the data? I'm not sure that they did.
So the very first model selection. So if I come back here, so I said we had it binned over time, and we'd get a Bayesian model. We'd get a probability of each source case for a time window. And then we'd take those probabilities, and those would be the prior for the next step. And we'd get the data from the next step, and then we'd do that. So that's how we got these model probabilities versus time. So this is time on the x-axis and model probability. Right. And so it was all background until this point, and then it jumped up and was source 1. And then it dropped down and was source 4 or whatever it was.
Did you consider running the same data through, but with time reversed, to see if you got the same answers or a discrepancy?
No, that would be really interesting. No, we did not.
Maybe take the average of the two would have gotten rid of it.
Augmentation, like reversing the data order or anything like that. That would have been a really clever idea.
I should have been on your team, obviously.
Yeah.
Oh, so I have another time question. I'll let somebody else ask questions. But the convolutional network approach, that seems like a pretty good idea for classifying and identifying the presence of detectors and which ones they are. Not so clear that it's great for the time localization. Did they do something specific for that, or can you say anything about that?
That's a good question that I don't know the answer on. So that team that for the public competition, that team that won the public one that had the CNN, I don't know how they picked out the time. I can't remember. I read a write-up they did on it. But I can't remember the name or the write-up, or I would share it with everybody right now. I can try to look it up and post it in the Slack or on the meetup if I can find it again. But yeah, and again, they were clever. They did some clever things with how they handled the making the image, the making the multiple images of different resolutions and then doing the CNNs across them and stuff. I don't know how they got the times right in that. I wish I could answer that for you. I'm sorry. I should have looked that up again, and maybe I'll kind of try right now while answering other questions. But now it bugs me that I can't remember that.
Yeah. Oh, just curious. That's cool. Thanks.
Yeah. Other questions? If you'd like, you can ask more of them, I guess, Bruce. If you had.
I think I'm good. Thought others might have some questions.
Okay. Yeah, so I actually, after the competition, I actually also learned. So I said we suspected, just because we knew the people, we knew of the people hosting it. We suspected the public test set was going to be harder to predict than the training data. That not just that they weren't they weren't completely overlapping. Probability distributions for the way they were sampled. That we knew that like the training data was going to be on some cases, and then there was going to be some harder cases in the public test set and some even harder cases in the private, is what we kind of, so we only suspected the test and the training. But when I got to talk to them later, they actually did do this. They wanted to see how different models extrapolated. So they did do this sort of thing. So they definitely sequenced they sequenced it to be harder and harder, which actually kind of got caused some grouchiness on some message boards and between some people on the public competition when the final results are posted, because the team that won crushed all the other teams. Like they were so far ahead on the public test board that, like, when the private test scores were revealed, they were still way ahead. They did, but like 2 through 12 or something totally reordered, and it mattered a lot because the money was not trivial. And so, like, I think whoever was in like second went down to like fourth or something. There was a lot of like swapping of positions among the top 10 or so, which mattered a lot for money and made for a lot of grumpy folks.
Leaderboard shakeup. It's a well-known phenomenon in the Kaggle world. I do have a question about the competition setup, which looked a little different from Kaggle. It seemed like you could submit a lot of submissions in one day. Was there a limit on how many?
There was a limit.
Because I think you said on the last day you submitted 44 times or something?
Okay. So the top code, the public one was more limited. The private one didn't actually have a limit. So we were submitting like crazy on the last day, and not private. By private, I mean the interlab one. So I said there was an interlab competition, and then they did the public top coder version. And the interlab one, they didn't have an amount on the last day. So we had like 44 submissions on the last day or something like that.
I see. So you were kind of using the interlab one as a validation set to some extent.
So the people running it were using the interlab one as they were using that as a way to make sure that the public one worked in kind of the ways they were hoping, as far as like the structure of things, and also just to make sure that they didn't have it just like they wouldn't put it up and like no one would do good at all because the model, like the data was just garbage or something. So they did use it as a little bit of a test bed, but so there were a lot of submissions on the last day, especially by the team that came in third. They submitted a ton of things on the last day. They were probably like 180 of these 250 or something. They just like submitted things like mad.
And the CNN team, you said they did so much better than everyone else. Do you remember roughly what their score was?
No.
I keep asking you these questions about that team. Sorry.
No, it's okay. Let's see if I can. Oh, do I not even have that up in the background here?
So 10,000 was the maximum, right?
Yeah, 10,000 was the maximum. So I also mentioned this. The scoring did change slightly between the two.
True.
Did I really close it and not everybody gets to see all the things I have, all the see if I can find it. Yeah, so look at this. You can see why the top ones reordering a lot mattered a bit for people. It's not trivial money for them. The top one's there. I'm signed into my personal Gmail instead of my work account. So I wonder if it won't even show me now with this. I might have to remember what my work account password is for Top Coder. Yeah. Yeah, I guess I can stop playing with this maybe, but this has got to be really boring for everybody for me to be.
Well, it might have popped up in a minute, but I guess it's always interesting to know with these competitions whether the sponsor was able to make use of the results afterwards. Did you have any idea? It's been a couple of years now since the competition was run.
So they've at least been able to publish something about the results. Man, I can't even type right now.
It's hard to type with an audience.
Here. Yeah, so this this is a write-up that was done about this. Statistical advice for design and analysis of data competitions. And yeah, so this was some of the folks that were involved in the design. This isn't everybody. Some of the folks were from Lawrence Berkeley lab also. I'm sure this is probably actually published somewhere too. Yeah, so here's that talking about the sketch of the sketch of that, how they were intentionally doing some of that, and they had a bunch of information.
Yeah, Bruce, I'm glad you asked about like the applications, because this sounds like oddly like a spy movie when someone's hiding like a nuclear bomb somewhere. Who's got to like run around, try to punch some guy to find out the location. But it seems like the model, you could drive a car somewhere down the city streets, you could probably find it by using the model.
Yeah, so if you live in the Bay Area, the San Francisco Bay Area, Lawrence Berkeley has vehicles that drive around the Bay Area, testing these models and stuff. They talk about how they can tell when they drive by places that have a lot of bananas and stuff, or like, bananas. They'll be able to detect, or like sometimes you can detect, like people who have had a CAT scan or something. If someone, you can get radiation dose off of the person that is detectable. Yeah, I guess I didn't mention the team that we lost to in the inter-lab competition, this Lawrence Berkeley National Lab team, Tenzing Joshi. They actually they work with people who do that like for a living, who do like methods for detecting cargo at port entries and stuff like that. Trying to look for something in a shipping container that ought not be there or ought not enter the U.S. That sort of thing.
Cool. Bruce, do you have one more question? It looks like you do.
No, I'm fine.
And the floor is open, so if anyone else has any question, I think this is your time to speak with Michael about this. Okay, it sounds like we have no one else asking questions, so let's wrap it up. First of all, Michael, thank you so much for presenting with us.
Thanks for listening to me ramble for an hour plus. So
no, it was great.
I asked everyone to unmute so we could give a round of applause. Shall we try that?
It's something that
yes.
I always
count us down, Matt.
I always think that's a risky thing to do in case.
All right, we're going to do it. It's very risky, but we're going to go for it anyways. All right, 3, 2, 1. Let's give them a round of applause, everyone. Yeah, that was
That was great.
Michael.
Thunderous.
Thank you.